So the second topic in A21 is called Enthalpy, Entropy and Free Energy. So just looking at the title, clearly we've seen enthalpy before. We've looked at it in energetics in AS2. The last topic we looked at was last enthalpy. But we've got two new terms as well, entropy and free energy. So clearly there's a bit of new stuff in this topic as well. In terms of what the topic's all about, it's kind of described in the first sentence there. It's examining the reasons why some reactions occur quite easily, while other reactions do not. Normally in chemistry, we only really concentrate on the reactions that do occur, so it's probably not something you thought about before. But different combinations of chemicals and conditions sometimes just don't lead to anything happening. Some reactions just don't occur in the way you might expect them to, or at all. So this topic's about examining why some reactions can happen and some reactions just don't happen. The first topic I think sort of builds on that. When we're talking about things that do or don't happen, the technical term for that is whether they're feasible or not. So the redefinition at the start there, a reaction that can occur is a feasible reaction, meaning you can get products from the reactants. It doesn't necessarily mean it's going to happen instantly. As you know, some reactions require quite a high activation energy. All it means is if you give that activation energy, you will get a reaction happening. Other reactions, no matter how much energy you put into them, heat them up really, really hot, still nothing will happen. They're not feasible. An example for that is the combustion of carbon. When you react carbon with oxygen to make CO2, it doesn't happen at room temperature. Obviously you need to heat it up, but it is a reaction that will take place quite easily. It's a feasible reaction. However, turning that round, if you get carbon dioxide, you're not going to be able to turn it back into carbon and oxygen. It's not feasible. Even if you heat it up really hot, nothing will happen. The reaction will not proceed. So an example of a feasible reaction, an example of a not feasible reaction. So if we're trying to think about maybe explaining why some reactions are feasible, not feasible, we have to think about what we already know. One thing that clearly is important about whether a reaction proceeds or not is the enthalpy change for the reaction. Because we're quite familiar with the fact that lots of reactions we've looked at, whether that's neutralization reactions, reactions of metals, things like that, generally they're quite exothermic. And that's true. Having an exothermic reaction is a good clue that reaction is feasible, and it's one of the main reasons why a reaction might be feasible. It's not too hard to think about why that is. If you think back to the enthalpy diagrams we looked at in AS2, in energetics, when something's exothermic, if this is energy going in this y-axis, you've got your reactants at the start, which have a certain amount of energy, and your products at the end have a certain amount of energy. In an exothermic reaction, heat is given out, and it's given out because your energy of your products is lower than the energy of the reactants, so the excess heat is given out. That is favourable because what you end up with at the end in your products have a lower energy than the reactants. So energy has been lost to make the energy lower for the products. If you've got a lower energy, you're generally more stable. So exothermic reactions lead your chemicals becoming more stable, and that therefore is favourable. So looking at the sentence here, one factor that determines whether a reaction is feasible or not is the enthalpy change. Highly exothermic reactions that give out heat energy, e.g. combustion, like that carbon example, tend to be feasible. And you might think that's it, that's the only factor, that the only way you can know if something's feasible or not feasible is whether it's exothermic or endothermic. Unfortunately, it's not quite as simple as that. They're less common, but you can get some endothermic reactions that also occur spontaneously, and therefore they're feasible. There's an example here. This is ammonium carbonate with ethanoic acid making ammonium ethanoate and carbon dioxide plus water. It looks a bit complicated. That's just a GCSE reaction. That's a carbonate, that's an acid going to salt plus carbon dioxide plus water. If you look at the delta H value for that reaction, it's got a positive sign, therefore it's an endothermic reaction, and that reaction will occur spontaneously. You can actually prove that for yourself in your own house. You can do a very similar endothermic reaction. And this is quite a nice excuse to do some practical chemistry, a little kitchen chemistry. All you need is a cup, and you need to root round in your cupboard and find some sodium bicarbonate. Sodium bicarbonate is what you use for baking. It's actually sodium hydrogen carbonate, which is just a variant on sodium carbonate. So it's a white powder, put it in the cup there. It's also called bicarbonate of soda. You might see that in your cupboard, or baking soda. So that's a carbonate, or hydrogen carbonate. I'm going to add some vinegar to it. Remember, vinegar is just a form of ethanoic acid. And this is a reaction we've looked at before. Acid plus carbonate goes to salt plus carbon dioxide plus water. So hopefully we'll see that happening in front of us. And I just about didn't add too much there. Now, There's nothing too spectacular about that. That is just fizzing. It's making carbon dioxide. Clearly it's a favourable reaction because it's proceeded without me having to do anything to it. The interesting thing about it though is if you touch the side of the glass, it actually is cold. It's a very favourable reaction, it happens very quickly at room temperature. However, it does take heat energy in from the surroundings. What this tells us is that enthalpy change can't be the only thing that will determine whether a reaction takes place or not, because this is unfavourable in that you require energy in from your surroundings and the products are now higher energy than the reactants. But there must be some other factor that does make this favourable, and that's what we need to look at in this topic. And that point's discussed in our notes just at this paragraph here. If you've got endothermic reactions which can occur, this means that the enthalpy change cannot be the only factor that determines whether a reaction is feasible or not. The other factor, which we're going to look at in this topic, which determines the feasible reaction is the entropy change. Now that's probably not a word you really encounter that much, but we're going to look at it now. The reaction above between ammonium carbonate and ethanoic acid is feasible because there's a large increase in entropy. So to summarise it all down, what we're saying is if a reaction is feasible or not feasible is determined by two main factors. One of those is enthalpy change, where it's favourable for you to have an exothermic reaction. However, the other factor you've got to worry about is the entropy change, and as we'll find out, if you have a large increase in entropy in a reaction, that can make the reaction favourable as well. It's a balance of two different factors in terms of feasibility of a reaction. Okay, so if entropy is important for reactions, you need to actually look at what entropy is. You may have heard it as a term before. It's kind of more associated with physics rather than chemistry, but we do touch on it here. It's quite a complicated concept if you go into it, but we can just go through that at kind of surface level. Entropy is given the symbol S. It's a measure of the disorder or randomness in a system. So in other words, if your system, a system just means like a container of particles or like a reaction, something like that, something you can actually study from the outside. If it's very disordered, it's called high entropy, and if it's very regular and ordered, it's called low entropy. It's always going to be favourable for you to increase entropy in the process. Second paragraph there, all substances possess a degree of disorder due to the constant movement of particles. This means all entropy values are positive. So that means even if you've got like a very ordered solid, because the particles are still vibrating, there is a small amount of disorder there. In other words, the lowest entropy you can get to is 0. You can't get negative entropies, and everything generally has a positive entropy. The entropy can increase or decrease over the course of a reaction depending on whether the particles become more or less disordered. This next point is very important. It's always favourable for entropy to increase, and that's true in chemistry, it's also true in physics and just general life. A little kind of example here for you, it's similar to one described in your notes. If you take a stack of coins and line them up all together like this, and if you try and drop them level onto a table, you're hoping to try and get them to stay in the pile, but no matter how often you do it, they're always going to spread out and drop. That's actually an example that demonstrates why it's always favourable for entropy to increase. Because when I had them at the start, they were all very ordered, they were in a nice neat line, but when I dropped them, they immediately collapsed into a state where they were all randomly spread out and they're currently very disordered. It's favourable for that process to take place. Putting that another way, you could describe it as they're energetically more stable when they're in a disordered state. And at that level we can kind of leave it. If you're happy that entropy just means disorder, and if you're happy that it's always favourable for entropy to increase, you're fine for this topic, that's all you need to worry about. Just to go off on a wee tangent, some of you might be a wee bit kind of suspicious of that, because that maybe implies that these pound coins have some sort of knowledge about what they want and choose to turn into a disordered state. It's actually more about probability rather than about like kind of chemistry or physical processes. When I have them in this stacked formation, all lined, there's really only one combination they can be in. So there's only one way of arranging them in this sort of straight line. However, when I drop them, there's no end to the number of combinations they can be arranged in now. They could drop like that, like they did here. They could drop like this. They could drop like this. So we're comparing one orientation for them being in a stack versus millions of orientations for them being strewn across the table. So just in terms of probability, it's always more likely you're going to transition to a place where you've got more options for how they sit. So entropy is a bit more about kind of probability. It's always more likely you're going to transition to something where there's lots of options for you to occupy rather than like only a couple. But as I said, as long as you're happy with those two main points, entropy is disorder and it's always favourable for entropy to increase. you're absolutely fine here. Increasing entropy can also be used to explain why ice melts at room temperature, because the water particles are able to spread out in the liquid more, so it's more favourable for them to do that and to melt. And why the smell of perfume will increase or will spread throughout the room. So they're very ordered if they're just sitting in one pocket of a room, but they're very disordered if they're spread out across all parts of the room. So what we're going to look at in the next video is how we can analyse reactions to maybe try and see if the entropy is going to increase or decrease, and then tie that together with enthalpy to work out whether reactions will be feasible or not feasible.